A very good morning. Today, we will be presenting about angular speed, acceleration, and tangential motion. First, my name is Diluvia Natunga Alexander Linggi, and I will be explaining about angular velocity. Angular velocity is a vector quantity that describes both the rate of rotation and the direction of the rotational axis. It uses the same formula as angular speed, but also indicates direction as in clockwise or counterclockwise.
If I hold it like this and I let it go, what will happen? It will drop. Why? Gravity. Boring. We start spinning it. Ready? I drop it. And it stays.
No, what?
What's happening? What's happening? It's a gyroscope now. It is spinning and it is precessing like our planet Earth.
In this video, a spinning bicycle wheel is suspended from one end of its axle, and instead of falling straight down due to gravity, it stays horizontal and slowly rotates around the suspension point. This happens because the wheel has angular velocity. It is spinning around its central axis, which gives rise to angular momentum, a property that resists changes in the direction of rotation. When gravity exerts a downward torque on the spinning wheel, so instead of simply causing it to fall, it causes the direction of the angular momentum to change gradually, resulting in a motion called precession. This demonstration visually shows how angular velocity influences the physical behavior of rotating objects, perfectly illustrating the principle of rotational motion and conservation of angular momentum in real life. So the angular velocity formula is angular speed equal to angular displacement over time. So here is two example of the question. So let us try the question. While riding a bicycle, a student observed that the front wheels makes 8 full rotation in 12 seconds. A. Calculate the angular speed of the bicycle in radians per second. So basically we just fill in the amount into the formula. So angular speed equal to angular displacement over time. So angular speed equal to 16 pi over 12 and is equal to 4.19 rads. B. If the wheel continues spinning at this rate, how many radians will it have rotated after 30 seconds? So it's already give you the time there. So angular displacement equal to angular speed times with the time. So angular displacement equal to 34 pi times with 30. So it's equal to 40 pi. And change the unit to radians. So it is the final answer, which is 125.66 radians. Next, we will move to angular acceleration.
Hello, my name is Leona Etilia Lilife. My metric number is PS231100181. So, in this slide, I will present about the angular accelerations. The definition is a uniform when an equal change of velocity takes place in equal intervals of times. However, small this may be, or the acceleration of a body is a rate of change of velocity. In this slide also, it contains a graph which is the speed versus time. First, the object experienced constant accelerations. The speed increased steadily over time, shown by the straight upward slope. Next, there is a horizontal line, meaning the object moved at a constant speed, no accelerations. Finally, the line sloped downwards, indicating constant decelerations, where the speed decreased steadily until it reached zero.
I want you to picture this. You have a wheel that is in front of you, and the wheel is currently just sitting still. But what happens is you flip on a switch, and the wheel starts moving faster and faster and faster and faster and faster, and you want to measure the rate at which this speed of the wheel is changing. Now I'll go ahead and assign some numbers here. So the wheel starts at 0 radians per second, and then 5 seconds later, the wheel is moving at 30 radians per second. To calculate the average angular acceleration, which is represented by the symbol alpha, all it's going to be is a change in angular velocity divided by the change in time. We start at 0 radians per second, we finish at 30 radians per second. If we take 30, which is our final angular velocity, and subtract out 0, I want you to picture this. You have a wheel that is in front of you, and the wheel is currently just sitting still. But what happens is you flip on a switch, and the wheel starts moving faster and faster and faster and faster and faster, and you want to measure the rate at which this speed of the wheel is changing. Now I'll go ahead and assign some numbers here.
Moving on to the next slide, which is they have two types of accelerations, which is positive accelerations and negative accelerations. Accelerations like a speed that can be positive or negative. So the sign of acceleration tells that how the velocity is changing. A positive acceleration say that velocity is increasing in the positive directions, where the negative accelerations is when the object is moving in the positive directions, but the rate of change of velocity is negative. Next is formula of accelerations. As I mentioned it before, the accelerations formula is accelerations equal to change in velocity delta v, or it can be delta w, over change in time, which is delta t. So the unit of acceleration is ms negative square. In this last two slides it contain questions which is for understanding and to solve the problems. So example 1 is a truck goes from a speed of 40 meters second to 70 meters second in 10 seconds. Find the acceleration of the truck. So the keyword is 40 meters second to 70 meters second in 10 seconds. So the 40 meters second is initial velocity, while the 70 meters second is final velocity. So the total velocity is 70 meters second minus 40 meters seconds equal to 30 meters second. So the accelerations is equal to 30 meters second over 10 seconds equal to 3.0 meters seconds negative square. Last slide is the example 2, which is a car accelerations from race to a speed of 36 km per hour in 20 seconds. What is the accelerations of the car in meter per second square? So the 36 km per hour is the velocity, but it need to convert to meter seconds, which is to convert it 30 km per second times with 1000 meter over 3600 second equal to 10 meter per seconds. So the accelerations is equal to 10 meter per second over 20 seconds equal to 0.5 meter per second square.
Tangential motion refers to the movement of an object along a circular path. But here's the key. At any moment, the object's motion is in a straight line that touches the circle. We call that line a tangent. A great example is point on a spinning tire. It's constantly changing direction, yet at every instant it follows a straight line along the edge. So, what exactly is tangential velocity? It's how fast an object moves along that tangent line. Even though the object is rotating, the speed at which it would move straight, if released, is what we call its tangential velocity. It's the link between spinning motion and straight line motion. We can calculate tangential velocity with the following formula, where v is tangential velocity, r is the radius of a circular path, and W is angular velocity. This equation helps us understand how fast something is moving in a straight line at any moment during rotation. Let's try an example. A bicycle wheel has a radius of 0.4 meters and spins at 5 radians per second. Using the formula, we can insert the values and get the answer 2 meters per second. So, the point on the edge of the wheel is moving at 2 meters per second in a straight line at that moment. Now let's reverse the problem. A toy car's wheel has a radius of 0.15 meters and the tangential velocity is 3 meters per second. To find the angular velocity, we will rearrange the formula and then insert the following values. We will get the answer 20 radians per second. This shows how we can switch between linear and rotational values depending on what we know.
We will see the differences between angular speed and tangential motion. Let's start with angular speed, also called angular velocity. It tells us how fast something spins or rotates around a center point. For tangential motion, this refers to the linear speed of a point on the edges of a rotating object. So, what's the difference? Angular speed rotational around center, while tangential motion linear at the edge. Then angular speed have same for all points, while tangential motion is bigger if farther from center. Then angular speed measure in radians per second, while tangential measure in meters per second. For example, for angular speed is spinning fence motor, while example for tangential motion, the blade tip moving through the air. So remember, angular speed is how fast something spins, and tangential motion is how fast a point moves along the edge. Alright, now let's try applying what we have learned about angular speed and tangential motion. Here we have two wheels spinning at the same angular speed, which is 5 radians per second. Wheel A has a radius of 10 cm, wheel B has a radius of 20 cm. But even though both are spinning at the same rate, will their tangential speed be the same? Let's use the formula V equal to R dot omega. For wheel A, radius is 0.10 meters, so V equal to 0.10 dot 5 equal to 0.50 meters per second. For wheel B, radius is 0.20 meters, so V equal to 0.20 dot 5 equal to 1.00 meters per second. So even though both will spin at the same angular speed, the one with the larger radius will B has the greatest tangential speed. This proves that tangential speed depends on both the radius and angular speed. Now, let's try another quick example together. We are given a point on a rotating disc that has tangential speed of 4 meters per second and the radius of the disc is 0.5 meters. We need to find the angular speed, which is how fast the object is rotating, measured in radians per second. To solve this question, we use the formula W equal to V over R, where W is the angular speed, V is the tangential speed, and R is the radius. So let's plug in the value. W equal to 4 over 0.5 equal to 8 radians per second. That's the angular speed.
Next, I'll be talking about the applications of angular and tangential motion in real life. Let me show you how these two types of motion appear in mechanical systems, and you can actually see them around you every day. Let's start with something simple, the ceiling fan. It rotates around a fixed axis, and when torque is applied, it causes angular acceleration. That means the fan's angular speed, or omega, increases. The blades farther from the center move faster in terms of tangential speed, and that's what pushes air around the room, helping cool it down. Next, the bicycle wheel. When you pedal, torque from your legs is transferred through the gears. This gives the wheel angular velocity, which drives the bike forward. At the same time, the wheel builds up angular momentum, which actually helps stabilize the bike. That's why you stay balanced better when riding fast. Now, let's move to tangential motion in a CD or DVD player. The disc inside spins at a constant angular speed, but the tangential speed isn't the same everywhere. That's because tangential speed equals radius times omega, so points farther from the center move faster. This is how the laser reads data from the inside to the outer edge along a spiral track. Finally, the roller coaster, an awesome example of tangential motion. As it moves along a curved track, it has tangential velocity at every point. The speed and how tight the curve is decide how strong the turning force feels to the riders. This shows how linear and curved parts work together in a circular motion.